Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will continue talking about complex numbers. Let z equal a plus ib be a complex number where a and b are two real numbers. The conjugate of z denoted by z bar is defined as z bar equals a minus ib. In other words, we leave the real part of z as it is and we change the sign of the imaginary part. So b becomes minus b. Complete the table below. This is z and this is z bar. Well, if z is a 3 plus 7i, what would be z bar? It will be simply 3 minus 7i, applying the definition. Well, if z bar is 2 plus I, what do you think z is? It will be 2 minus I. And if z is minus 5i, what would be z bar? It will be 5i. So as you see, we change the sign of the imaginary part. We leave the sign of the real part. This is 2, this is 2. But we change the sign of the imaginary part only. Well, if z bar is minus 7, what do you think z is? It will be also minus 7. So the conjugate of a real number is itself. This complex number, its conjugate would be half minus the square root of 3 over 2i. And finally, if z bar is 0, z also would be 0. So notice here, the conjugate of a real number is itself, whereas for the conjugate of a pure imaginary number, we just change the sign of the pure imaginary part. Let's see this application. We need to complete the table below. Remember, x and y are real numbers. This is also z and this is z bar. Well, if z bar is minus 3 plus 6i, try to find z. This is minus 3 minus 6i. If z is 4, try to find z bar. This is also 4. And if z bar is minus 2i, try to find z. It will be 2i. And if z is x plus iy, what would be z bar? This is x minus iy. And if this quantity is z bar, what would be z? It will be x plus 1 minus into y minus 1i. So we leave the real part as it is, and we change the sign of the imaginary part. Finally, if this is z, what would be z bar? It will be 2 minus ix plus 3i. Now let's see the properties of the conjugate of a complex number. Z is as usual a plus ib, where a and b are two real numbers. What is z times z bar? If we just expand here, these two quantities, we get a squared plus b squared. Remember, because I squared is negative 1. Now what is z plus z bar? This is a plus ib plus a minus ib, which is 2a. And z minus z bar, which is a plus ib minus factor a minus ib is 2ib. Now notice from here that z bar and z plus z bar are real numbers. As you see here, we don't have any I, whereas z minus z bar is a pure imaginary number. Now write each complex number below in algebraic form. Here we will see where do we use the conjugate of a complex number. Now this is z, it's not written in algebraic form. Remember, the algebraic form is a plus ib, so we cannot have I in the denominator. So what do we do in such a case? We multiply the numerator and the denominator by the conjugate of the denominator. So we multiply by 2 minus I, up and down, as you see here. And this looks like rationalizing the denominator that you took in previous classes. And in this case, if we just simplify, we get 2 minus I in the numerator. And this is of the form z into z bar, which is a squared plus b squared. So it will be 4 plus 1, which is 5. So this is 2 minus I over 5, and remember this is not also given in algebraic form, because for the algebraic form we have to specify A alone and B alone. This would be 2 over 5 minus 1 over 5 I. And in this specific case, A is 2 over 5 and B is negative 1 over 5. So where do we use the conjugate of a complex number? One of its usages is when we want to remove I from the denominator. Let's see this example. So we also multiply by the conjugate of the denominator, which is 3 plus 2i. For the numerator, we get this quantity after we expand, and for the denominator, we get a squared plus b squared, which is 9 plus 4. And this is what we get, and remember to write it in the correct form, which is 1 over 13 plus 5 over 13 I. Now this part, x and y are real numbers, so the conjugate in this case would be x minus iy. We multiply the numerator and the denominator. Pay attention here because we have many terms. This is what we get after we multiply and simplify. We try to write it in algebraic form. In this case, a is x squared plus y squared plus x over x squared plus y squared, and b is minus y over x squared plus y squared. Now let's see the application. You need to write each complex number below in algebraic form. Try to do this one alone. Well, if we multiply by the conjugate by I up and down, we get this quantity, which is 1 plus 2i. This expression, try also to do it alone. Pay attention for the conjugate. So the conjugate in this case would be x plus 1, the real part as it is, minus iy. We change the sign of the imaginary part. Now for the numerator, we get this expression. For the denominator, this is what we get. Try not to expand the denominator, leave it as it is, and this would be the final answer. The last part, try also to do it alone, take your time. Well, in this case, the conjugate would be x minus iy minus I up and down. This is what we get for the numerator, and this is for the denominator, and after simplification we get this expression. Let's continue talking about the properties of the conjugate of a complex number. Now we have two complex numbers which are z and z prime. Remember, z plus z prime quantity bar is z bar plus z prime bar. So we distribute this bar for the first complex number and for the second complex number. Similarly for subtraction and multiplication. While we continue, we can also distribute this bar when we have a division. So what is z over z prime quantity bar? It will be z bar over z prime bar. And remember here, z prime can never be 0 because it's given in the denominator. And as you expect, z bar bar is z. Now let's see the third example. Z is a complex number, and the question is to simplify. Let's simplify this expression using the properties. Remember, because we have minuses and pluses, we can distribute the bar on each term. So here we get a z bar minus 1 bar, which is 1, and plus 2i bar, which is minus 2i. So we distribute the bar on each term. Now this expression, also if we distribute the bar, we get z bar bar plus 3 bar, which is 3, and minus I bar, which is plus I, and z bar bar is z. Now for the third one, this one, we also distribute the bar for the numerator and the denominator. We get z bar over the bar of this denominator, which is z bar minus 1 quantity bar. We redistribute the bar in the denominator. We get z bar in the numerator, and in the denominator we get z bar bar minus 1, which is z minus 1. Now also z is a complex number, and you need to simplify Try to simplify this expression alone. Take your time. Okay, if we distribute it, we get 2 minus I bar times Z bar, because here we have a multiplication between I and Z, so we can distribute the bar, and we know that I bar is minus I, so this becomes 2 plus I Z bar. Now this expression, try also to do it alone. Well, we have multiplication in between, so we can distribute the bar on the two factors. This is the first factor, this is the second factor. Then we redistribute the bar on each factor alone. We get Z bar, which is Z, and plus I bar is minus I. And here we get Z bar plus I. Now let's see the fourth application. P is this complex number. The question is to verify that P times P bar is an integer to be determined. Try also to work it out alone. Well, what is P times P bar? If we just substitute, this is P and this is P bar. We try to distribute the bar on each term here. This is the first term, we leave it alone here. We distribute it on the numerator and on the denominator. For the denominator, we get Z bar minus 1, which is Z minus 1. Then if you just look at this expression, you can simplify Z minus 1 and Z minus 1, and we can also simplify Z bar minus 1 and Z bar minus 1. So we get nothing but 1, which is an integer. Now Z is A plus IB and Z prime is A prime plus IB prime, where A, B, A prime, and B prime are real numbers. Well, Z is going to be equal to 0. If Z is equal to 0, this means that A is 0 and B is 0, and vice versa. If A is 0 and B is 0, we can tell that Z is 0. And if we know that Z and Z prime are equal, this means that the real part is equal to the real part and the imaginary part is equal to the imaginary part. And the converse is also true. I mean, if the real part equals the real part and the imaginary part is equal to the imaginary part, this means that the two complex numbers are equal. And this is very logical. Well, Z and Z prime are two complex numbers, and X and Y are two real numbers. The question is to find X and Y in each of the cases below. Now this is Z, and we know that Z is equal to 0. So remember, if Z is equal to 0, this means that the real part is 0 and the imaginary part is 0 at the same time. So from here we can tell that Z is 0. 3x minus 6 is 0, and 2x plus y is also 0. And this is a system of two equations with two unknowns, and its solution is x is 2 and y is negative 4. And this is the answer to that question. Now let's see another example. This is Z. This is Z prime, and we know that Z is equal to Z prime. Try to go back to the property. Well, Z is equal to Z prime. This means that their real parts are equal and their imaginary parts are equal. So in this case, we can tell that this quantity is equal to that quantity. So x is equal to y, and y is equal to 3x minus 2. And if we reorganize the system, this is what we get. And after solving the system, we get x is 1 and y is 1. And now part C, this is Z, this is Z prime. We know here that Z prime is equal to minus Z. So if we just substitute, Z prime is minus Z, this is Z prime, this quantity, and minus Z is minus X minus IY. And by now I have two complex numbers that are equal. So the real part should be equal to the real part, and the imaginary part should be equal to the imaginary part. This is the system that we get. If we reorganize it, this is what we get. And finally, after solving this system of two equations with two unknowns, we get x is 4 and y is negative 3. Now, Amir or Rami, the question is to simplify this expression. Let's see what's happening. Amir said that this expression could be written as minus iz plus 1 plus 2I. So Amir changed the sign of every I, if we can say. I becomes minus I and minus 2I becomes plus 2I. Rami did it as minus iz bar plus 1 plus 2I. The only difference between Amir and Rami is that Amir wrote Z whereas Rami wrote Z bar. I think Rami's method is correct because if we want to distribute this bar, we have to distribute it on each number here, and I bar becomes minus I, and we have Z bar, which is written as Z bar, which is left as Z bar because we cannot simplify it anymore. So the mistake in Amir's method is that he didn't apply the conjugate on Z.